What if our universe is just a grand simulation, running on some super advanced computer? What if our three-dimensional world is nothing more than an illusion, a hologram, or even pure mathematics? Sounds wild, right? But how do we even begin to understand what reality truly is? Let's start with something simple. An apple. Is the apple real? You can hold it in your hand, smell its fresh scent, and taste its juicy flavor. You can see the vibrant green of its skin catching the sunlight. It seems pretty real, doesn't it? But what does it actually mean for something to be real? What exactly is reality? Our ancient ancestors probably didn't think too much about it. For them, reality was what they could see, hear, touch, and taste. It was all about survival, like hearing a twig snap in the forest, which could mean dinner or danger. Sensing reality was a matter of life or death. Perhaps, therefore, in their day-to-day struggles, these truly distant ancestors had little time to wonder, little time to think deeply about the world that surrounded them. But as humans evolved, so did our thoughts about the world around us. We started to wonder about life after death, spirits, and gods. These ideas hinted at something beyond the physical world, something more than meets the eye. We started burying our dead around 100,000 years ago, hinting at beliefs in an afterlife or something beyond the physical world. This was the beginning of deeper questions about existence. What they thought as they bid farewell to loved ones is unknown, but perhaps they imagined a world beyond our reality, an afterlife. As time went on, ideas about spirits, gods, and invisible yet powerful forces began to emerge. People started asking big questions about meaning and purpose. And of course, according to some beliefs, the gods even gave us the apple, providing delicious fruit for us to enjoy. Back then, there was no need to question the reality of the apple beyond this. The answer was simply beyond human understanding, known only to the gods. Yet some began to wonder more deeply. Fast forward to ancient Greece in Plato's time. Plato, one of the greatest philosophers of the ancient world, lived in Athens in the 4th century before our era. His real name was Aristocles, with Plato being a nickname meaning broad, referring to his stocky build. The material world troubled Plato. Where do objects get their properties, like the greenness of an apple's skin, or the fact that dogs have 4 legs? Plato argued that our world was not the real world. To understand this, we must explore his famous allegory of the cave. Imagine a group of people who have been chained to a wall in a dark cave since birth. They cannot turn their heads and can only see the wall in front of them. Behind their backs, a fire is burning, and between the fire and the prisoners pass people carrying various objects. These objects and people cast shadows on the wall of the cave, and the prisoners see only these shadows. For them, the shadows are the only reality. What are they to make of this external reality they can barely see? How are they to understand the real world? But we can go further. What if mischievous people are illuminating the cave wall with a bright fire, using shadow puppets to play out stories? No longer are the prisoners simply seeing people wander around the fire. Now they see stories of monsters, battles, castles, and kings. What are the prisoners to make of this new reality? Is it any less real than before? To them, the images on the wall are their reality. There is nothing else. These exciting tales are as real as the previous shadow people. Plato then asks us to consider that we are like the prisoners, and the reality we experience is a projection of a place where true reality exists, with our imperfect world being a shimmering image of perfection. Looking at what we know now, Plato's ideas were surprisingly ahead of their time. But in the grand story of reality, this was just the beginning. To truly uncover the secrets of the universe and reveal the ultimate truth about the nature of the cosmos, we needed to go beyond ancient philosophy and the realm of the gods. We had to dive deep into the fundamental makeup of matter, time, and space. We had to turn to the insights provided by scientific exploration. And let me tell you, when we did, things got strange. Really strange. In the early months of 1821, the poet John Keats died in Rome at the age of 25, his body ravaged by tuberculosis. In his short life, he was prolific, writing about the natural beauty of the world. Like many before and after, he was only truly recognized posthumously. Keats was born nearly 70 years after Isaac Newton's death during the Industrial Revolution, driven by Newton's insights into the natural world. The scientific revolution of Newton and his contemporaries sought to peel back reality, revealing it as a manifestation of physical law. Newton realized that the white light of the sun contained all the colors of the rainbow, and that water droplets in the sky spread sunlight in a glorious display from red to violet. The seemingly mystical appearance of one of nature's wonders had, Keats complained, been destroyed by Newton, reducing it to little more than a prism. In Keats's words, Newton had tried to unweave the rainbow. Newton's scientific achievements, which Keats saw as stripping the world of its poetic mystery, actually ushered in a new era of understanding nature, allowing science to gradually reveal the nature of reality. Let's think again about our apple. One defining characteristic of a ripe apple is its colorful skin. But where does this color reside? Apples are made of a complex mix of water, sugars, and more intricate structures. So why do we see the apple as green? To answer this, we must delve deeper into the meaning of color, beginning with the last man who knew everything. Thomas Young, one of the last great polymaths of the Enlightenment era, was born in the small Somerset town of Milverton in 1773. Precocious from the start, he learned multiple languages and was instrumental in deciphering Egyptian hieroglyphics after the Rosetta Stone's discovery. Young's name might be familiar as he conducted the first double-slit experiments. We will return to Young's double-slit experiment later. Artists knew that mixing colored paints produced new colors, and three colors, red, green, and blue, were particularly important. Young proposed that the eye contains three kinds of fibers, now called cone cells, one sensitive to red, another to green, and another to blue. The stimulation of each type of cell is passed along the optic nerve to the brain, where it is mixed like paint to give us the sensation of color. Things get strange when we look at the eyes of other animals. Our closest relatives, apes and monkeys, are similar to us, sensitive to three color bands. But most mammals have only two, equivalent to our blue and green, reducing their color palette. Would they see a banana as yellow? Bees have three color receptors, sensitive to blue, green, and ultraviolet. Reptiles, fish, and birds can have 4 or more color receptors. The mantis shrimp has 12 receptors across the rainbow, seeing the world in colors we can't imagine. What are we to make of this array of animal visions? For humans, the yellow of the rainbow matches the signal from a banana's skin, but other creatures might not agree. To them, a strawberry, broccoli, or human skin might be the same color as a banana. This tells us something profound about reality. Our sight is a shadow of reality, created by our brains. It is subjective, not objective. We live in a visual simulation of our own making, built from stimulations fed into our brains. Newton told us about raindrops and sunlight, but the colors of the rainbow exist only in our minds. The sounds we hear are similar illusions, interpretations in our minds of vibrating eardrums due to pressure waves in the air. We live in a virtual reality of our own making. So if what we perceive is not truly reality, then what is? Well, space and time can at least be trusted. The apple is here and now, that is one certainty. Or is it? For in the revolution that followed Newton and Young, no part of reality was safe. Time ticked by slower in the past than today. In 2023, astronomers measured just how much. Their focus was quasars from 12 billion years ago, black holes with masses billions of times that of the sun. In the intense gravity of these black holes, matter orbits close to the speed of light, heated to billions of degrees and glowing intensely across the universe. In the turbulent maelstrom before it vanishes into the hole, matter crashes and grinds, and the intense light brightens and fades like a cosmic firework display. Hidden in this flickering, astronomers found a subtle pattern, a special regularity, and realized they could use this quasar tick to measure the passage of time when the universe was young. They compared the tick of a clock today to the ticks of these quasars, finding that the farther away the quasar, the slower its ticks became. When the universe was a tenth of its present age, time ticked at a tenth of its current rate. This result was spectacular, but not unexpected, for this cosmic dilation was written into the mathematical laws governing the universe in a theory developed more than a century before, a theory that forever changed the reality of space and time. I think, therefore I am. These famous words were uttered by the French philosopher René Descartes, and this deep musing on the reality of being has reverberated through the centuries. But Descartes pondered more than just the meaning of being. One frigid night in 1619, Descartes found himself confined to a small room, bedridden with illness. As a young man, he had recently completed a brief period of military service with the Dutch States Army, which was not uncommon for educated men of his time. During this service, he had studied engineering and mathematics, but this night would be like no other. As Descartes lay there, trying to keep warm, he began staring aimlessly around the room. He spied a fly walking across the ceiling before launching into flight, darting about and settling on the wall. As the fly buzzed about, a thought crossed Descartes' mind. How could he describe the fly's journey? He realized he needed a reference point to anchor the fly's motion. While this point is arbitrary, it must be consistent and not change. He also realized that talking about the distance from this point to the fly is insufficient. He needed the direction to fully describe its motion. Then, a startling thought came to Descartes, a realization that would simplify the fly's motion. For his reference point, Descartes took the corner of the room where two walls met the ceiling. From this point, he imagined lines running along the joins, defining axes that meet at the corner at right angles. If you project the fly's location onto each of these axes, Descartes reasoned, you get numbers. These three numbers specify the fly's location at any instant, uniquely defining a location in three-dimensional space. These numbers change continuously with the ticking of the clock. Descartes' coordinate system seems obvious to us today. Children are taught to use it when they encounter location and motion in elementary science. For professional scientists, laying down a Cartesian coordinate system is the start of finding solutions. Descartes' name continues to reverberate through the centuries. Dying in 1650, Descartes was unaware of a young boy growing up in the English countryside. This boy, Isaac Newton, would grow to use these notions of time and three-dimensional space, laying them down as the mathematical stage on which all motion takes place. It was Isaac Newton who laid out the rules we now call classical mechanics. In Newton's universe, time is a true absolute, a single clock that ticks across the universe, a tick that everyone agrees on. Space was slightly more complicated, as Descartes' contemporary Galileo had discovered, as each observer has the freedom to define the origin of their own coordinate system. Galileo thought more in terms of stories than in the mathematics of Descartes or Newton, and he laid out his notions on motion by thinking about being on board a ship. He realized that if the ship was in a harbor or sailing smoothly on a glassy sea, the experience below deck would be identical. However, if the wind picked up and the ship began to speed up or sailed into choppy waters, the ship would rock and roll, and those below deck would feel this change in motion as plates and cutlery slid off tables and people became unsteady on their feet. From this, Galileo declared that there must be no absolute rest in the universe. All motion, he said, must be relative, and the laws of motion must be the same for observers in a state of unaccelerated motion. The first theory of relativity had arrived. These ideas are reflected in Newton's equations of classical mechanics. Every observer in uniform motion can use Newton's three laws to calculate the outcomes of experiments. It's easy to test this yourself by dropping a ball on a train station platform and seeing it fall to the floor. Repeat this experiment on a train traveling at uniform constant speed, and again the ball will simply fall. If, however, you drop the ball at the start or end of the train journey, the train will be accelerating up to speed or slowing down as it approaches its destination, and dropping the ball at these times will see the ball veer towards the back or front of the train, seemingly defying Newton's laws, as no forces are pushing in these directions. These fictitious forces only appear as your coordinate system is accelerating, and they vanish as soon as you achieve uniform motion. This picture of the background of reality existed for several centuries until a Scottish physicist, James Clerk Maxwell, finally unraveled the mystery of light, and with it, the bizarre reality of our universe. Maxwell's impact on science was enormous. By the mid-1800s, Maxwell had mathematically united electricity and magnetism. There had been experimental clues that these phenomena were related, but in a handful of equations, Maxwell showed that they were one and the same. This was already an immense achievement, one for which Maxwell would become scientifically famous. But he looked deeper into his equations and realized they implied something profound. Light itself must be an electromagnetic phenomenon, oscillating and intertwined fields of electricity and magnetism. His equations also revealed the speed of light, a blistering 300,000 kilometers per second, but curiously, not what this speed is relative to. By whose coordinates was this speed determined? It seemed that a notion of absolute rest would be needed to save physics. Some proposed an absolute background, an ether, in which light propagated throughout the universe, and experiments were created to test the idea. This included experiments bouncing light rays off mirrors or sending a current through an electrical circuit and lighting a bulb. The outcomes of these experiments would depend on the motion relative to the ether, and were built to demonstrate that the universe must possess an absolute state of rest. However, this would be a serious headache for Galileo's idea of relative motion. Why would electromagnetism know about this state of rest, while the rest of physics didn't seem to care? Why would Galileo's relativity hold for everything except electromagnetism? Why would the physics of reality have to be so complicated? In 1905, one physicist stated that it didn't have to be so messy, that the universe was not split into some physics that obeyed Galileo and some that didn't. No, electromagnetism had to respect relative motion also. And so, at the start of the 20th century, Albert Einstein's special theory of relativity was born. At its core, the special theory of relativity reflects the dream of the lazy physicist, the dream of explaining as much as possible with as little as possible. Einstein demanded that all observers, irrespective of their relative motion, can use Maxwell's equations to calculate the outcome of electromagnetic experiments. But this comes with an uncomfortable consequence. All observers must measure an identical value for the speed of light. This was simply not possible with Newton's notion of space and time. And so, space and time, Einstein claimed, are not rigid or absolute. Instead, they must be flexible, such that times and distances depend on who is observing them. This sounds like lunacy. Indeed, this is not the experience of our everyday lives. But experiments close to the speed of light reveal this distortion of space and time. In the 1960s, irrefutable evidence for the twisting of time was found. The focus was on a subatomic particle known as a muon, effectively a heavier version of the electron. Unlike the electron, which lives forever, muons only last for 2/millionths of a second before disintegrating into electrons and neutrinos. Physicists knew that high-energy muons were made in the upper atmosphere, created when particles from deep space smash into gas molecules. As they travel close to the speed of light, the muons should have traveled half a kilometer before decaying. But physicists detected muons arriving at the ground after traveling many tens of kilometers. Why were these muons lasting so much longer than their lifetime suggested? The answer lay in Einstein's special theory of relativity and a quantity known as the Lorentz factor, which dictates the dilation of time. To explore this, we must understand the immediate consequence that sprang from the special theory of relativity. The speed of light is an absolute speed limit to the universe. No matter how hard we try or how much energy we have, no object with mass could ever reach the speed of light. The Lorentz factor depends on the relative velocity, but as speeds get closer to that of light, the Lorentz factor grows unbounded. So, for the muon, its life is over in just 2/millionths of a second. But for the physicists on Earth, the muon's life appears much longer, allowing it to reach the ground. Of course, there is a flip side to this story, the other side of Einstein's strange relativistic coin. The physicists see the long-lived muon traveling tens of kilometers before decaying. But if you could ask the muon, it would say it had only covered a few hundred meters in its short life. Space, as well as time, can be distorted and dilated when speeds approach that of light. Einstein also realized that this speed limit had profound implications for information, as it could not be transmitted faster than light. A classic example is that we don't see the sun as it is now, but as it was 8 minutes ago. The light we see from the Andromeda galaxy set off before humans walked the Earth. Through their telescopes, astronomers see galaxies as they were billions of years in the past. Indeed, the universe as it is now is completely hidden from us. We only see it as it was in the past, along what is known as our past light cone. The further an object is, the younger it appears. Other consequences from Einstein's view began to flow, where time and space mean different things to different observers. Without the absoluteness of Newton's time, there is no universally agreed now, and the relative nature of time means that observers disagree on how much time has passed. Einstein immediately realized that this doomed a cherished idea, the idea of synchronicity. This is the notion that two events at two different locations happen at exactly the same time. We experience this every day. It is part of the rhythm of life, where things happen at certain times. But this is all an illusion. To understand this, let's take a look at one of Einstein's thought experiments. Imagine a train moving at an extremely high speed. Inside the train, there are 3 individuals, one at the back, one at the front, and one in the middle. They decide to conduct an interesting experiment with light. The person in the middle has a device that can emit a pulse of light in both directions at the same time. The individuals at each end have mirrors and are instructed to raise their hands when the light reaches their mirrors. From the perspective of those on the train, everything seems straightforward. The light reaches both ends at the same time, reflects off the mirrors, and returns to the middle simultaneously. It appears that the people at the ends raise their hands at exactly the same moment, in perfect synchronicity. But let's now think about the view of an outside observer, not riding the train, but standing on the platform. For fun, let's make the train move very fast, close to the speed of light. What does this outside observer see as the train roars by and the experiment unfolds? This is where it gets a little odd. Our outside observer sees the experiment begin and the pulses of light heading along the carriage. But remember what Einstein's special relativity demands. All observers see light travel at exactly the same speed, the speed of light. What influence does this have on what our outside observer sees? As the train moves, the back of the carriage reduces the distance the light has to travel, while the front of the carriage moves away, increasing the distance to the reflecting mirror. The light eventually bounces off each mirror and makes its way back to the middle, with the distances changing again. Eventually, both pulses make it back to the middle at the same instant. But when the outside observer is asked what he saw, how would they describe the experiment? He will say they saw the pulses emitted at the same time and arrive back in the middle at the same time, but he saw the reflections and hands being raised at different times. Synchronicity depends on who is observing. Einstein was thrilled with his special theory of relativity, but he hit a snag: gravity. Back in the 17th century, Isaac Newton gave us his famous equations to explain gravity. They worked great for things like apples falling from trees or the moon's orbit. But there was a catch. Newton's equations relied on the distance between objects, assuming time was absolute. In his world, you could pinpoint a precise now to measure that distance. But Einstein's universe was different. In his view, now wasn't a fixed point. So how could he fit Newton's gravity into his theory? He couldn't. This led him to rethink gravity entirely. Imagine having to start from scratch. Einstein realized that both time and space were flexible, like a cosmic fabric that could bend and stretch. After a decade of hard work, he cracked the code in 1915 with his general theory of relativity. Now, gravity wasn't just a force between masses, it was the curvature of space-time itself. This breakthrough helps us understand everything from the expanding universe to how GPS works in our daily lives. Fast forward to 2023, and we're still exploring these mind-bending ideas. Have you heard about the quasar study? It suggests that time might have run slower when the universe was young. If you were there back then, a second would feel like a second. But as the universe expands, light stretches, making the distant past seem to tick by more slowly. It's like watching an old movie in slow motion. This concept is similar to what happens around black holes, where time slows down dramatically due to extreme warping of space-time. Einstein's revolutionary view changed how we see time forever. It's personal and relative. Your clock, whether it's a watch or your heartbeat, ticks at its own pace. But someone else's clock might tick differently if they're moving at a different speed, in a different gravitational field, or even in a different era of the universe. This bending of time is part of the cosmic dance. Just think about those long-lived muons hitting Earth's surface, or atomic clocks that desynchronize after a trip around the planet. They all show how time can vary. As you pull your focus away from the vastness of the universe, you bring your attention back to the apple in front of you. You are certain that the apple exists here and now, just a couple of meters away. Yet you must acknowledge that your now is uniquely yours, a personal slice of reality. What constitutes the world around you? How would you dismantle the universe? Remember, questioning reality isn't just for philosophers and scientists. It's for all of us who want to understand the incredible world we live in. So keep asking questions, stay curious, and who knows, maybe you'll be the one to uncover the next big secret about the nature of our reality.